So Graham, for those who don't know, what are organic semiconductors?
Organic semiconductors are a special class of plastics that have some quite unusual properties. Unlike most plastics, these materials can conduct electricity, and they can also be stimulated optically or electrically to emit visible light. The materials are now widely used commercially as organic LEDs or OLEDs in the displays of mobile phones and smart TVs. The Organic Semiconductor Centre in St Andrews is a collaboration of physicists and chemists who are developing new materials and new applications. We study the fundamental science of the materials and how light interacts with them, and how they can be used to make LEDs, lasers, solar cells and sensors. We are also developing applications in smart lighting, in medicine, in communications, and as sensors for detecting explosives.
How can they be used to detect explosives?
Well, it turns out that the same materials that are used for OLEDs can also be used as trace gas detection sensors for explosives. A thin film of the light-emitting polymer, if it's illuminated with UV light, will re-emit fluorescence in red, blue or green depending on the material. But if a TNT molecule comes into contact with the film, it can act to interrupt the light emission process, thereby reducing the fluorescence that's emitted from the film. By monitoring this drop in fluorescence, we can detect trace levels of vapors of explosives in a similar way that a sniffer dog would. So Ross, what is the motivation behind the work?
For landmine detection, for example, there are existing methods that work quite well, like metal detectors, sniffer dogs and things like that, but they're not ideal for all types of terrain or climates. But with the types of materials that we're using here, we can really complement those by sampling the vapour, eventually being able to detect landmines or IEDs or bomb factories.
And how are the sensors made?
So the big advantage with these sensors are they're solution processed, so they're relatively easy to make. Where we make a solution, we can spin coat it onto a glass slide, and from there we can illuminate them with a laser or an LED to watch for that telltale signature of an explosive with the drop in light emission. So what's been the pathway to generate impact?
Well, our research started as a basic scientific study of how nitroaromatic molecules can quench the light emission from thin film organic lasers. We then joined a large European project which was developing many different tools for humanitarian demining actions. And this gave us an opportunity to get talking to end users for the first time and to learn how our science could be applied for in a real world scenario. We subsequently used EPSRC Impact Accelerator funding to adapt the technology, to further engage with end users, and to undertake initial field trials for detecting IEDs. To get our research on sensors into the real world, it's crucial that we build networks across Europe and the rest of the world with the people who would actually be the end users for the technology.
Yeah, to me a hugely important part of this work is being able to take our technology for pesticides and explosive sensing out to the end users.
By finding out how well they work in these environments, we can adapt our sensor platforms to work better and be fit for purpose. We hope this will improve the way trace explosives can be detected in the future.
And this research is really intended to help public health and safety, society, quality of life and the environment by helping people clear away landmines from landmine afflicted areas, IED related explosives or hazardous pesticide pollution in public water networks. So we conduct regular field trials, especially with our collaborators in Croatia, who we've worked with for quite a few years, where we go out onto test minefields, where we can actually test this stuff in the environment it's supposed to be used. And having that kind of collaboration is invaluable. We have a project with them at the moment where we're even using honeybees that can fly around and pick up explosives on their bodies from landmine afflicted areas, and we can sample that air from the hive and then expose that to our sensors and tell if there's a contamination problem for landmines in that area. So what does the future hold?
Organic semiconductors are a fascinating material to work with, and their role in sensing dangerous chemicals could in the future have a truly global impact.